So we now want to solve the eigenvalue equation n acting on psi n is equal to small n times psi n. We want to find out what these eigenvalues small n are. So to do that, we need some properties of these operators n, a, and a dagger. So let's do that. Now, like the Hamiltonian, it's easy to show that n is also a positive definite operator. We have already seen that n is Hermitian. That means that its eigenvalues are real. But if I take n and take its expectation value with respect to some state psi, then this is going to be psi a dagger a acting on psi. But we can move this over here, and then this will become a of psi, but this is nothing but the modulus of the state a psi squared, which is of course greater than or equal to 0. So thus we say that n, which is an operator, is a positive definite operator. It also means that its eigenvalue spectrum will be 0 or greater than 0. So that's one thing to start with. So next, let us figure out what is the commutator between a and a. So remember, n is a dagger a. So now we can use an identity. This is a very useful identity for commutators, which is if you have product of two operators and we evaluate the commutator of that product with another operator, then we can write this in terms of commutators of the individual operators. To see this, let's write this out fully. And then what we can do is that we can subtract one term, this term, and then I can add this term. So this term was not there before, but I'm subtracting and adding the same thing. Then these two first terms can be written as a times the commutator of b and c. And the second and the last two terms can be written as the commutator of a and c times b. So using this, we can now express n, the commutator between n and a, as a dagger commutator of a with itself plus commutator of a dagger and a with a times a. Of course, the commutator of any operator with itself is 0, so the first term gives us 0. The second term gives us 1 times a. And therefore, we find that n times the commutator between n and a is plus a. So we made a mistake here, and the mistake was that a dagger and a is not plus 1 but minus 1. So this should be a minus 1 and this should be a minus sign here. So this is our first important commutation relationship. So using the same logic, we can evaluate the commutator between n and a dagger, and that's going to give us plus of a dagger. So these are the two very important commutation relationship that we will need. So let's look at what are the effects of a and a dagger are on states, and therefore what the interpretations are. So n acting on some eigenstate psi of n gives us small n psi of n. Now if I apply a on psi of n and ask what is the eigenvalue of this new state, to find that we apply the n operator on this, and then we use this commutation relationship and write this as a times n minus a acting on psi of n. But a times n is a n psi of n minus a psi of n, but n acting on psi of n will give me the eigenvalue small n. Therefore, we can factor that out the n minus 1 times a of psi of n. Thus, we see that the effect of applying a on psi of n is to make it into the state which has the eigenvalue n minus 1. So this state, so we can write the proportionality constant as C n minus 1 psi n minus 1. So here we are going to assume that all our states are normalized so that we get the inner product between psi n and psi m will be delta mn. So this proportionality constant will play an important role, as we shall see soon. Similarly, if we apply a dagger on psi of n, what happens to this state? So now we can apply again n on it, and then similarly using the second commutation relationship, and remember that there's a plus sign here, we get a dagger n plus of a dagger acting on psi of n, right? And so the first term gives us a dagger small n plus a dagger acting on psi n, and therefore we get n plus 1 a dagger psi of n. In other words, the effect of a dagger on psi n is to change the state to psi n plus 1. It increases the n eigenvalue by 1 unit, and therefore we can write a dagger psi of n is some proportionality constant, let's call it d, n plus 1, then psi n plus 1. So these are important relationships. Now observe that a dagger raises the n eigenvalue by 1, and a lowers the n eigenvalue by 1. So that's why a dagger is called the raising operator, and a is called the lowering operator. And together they're called ladder operators. So we need to determine C and D. So to do this, let's start with the inner product between two states, psi m and psi n. And we have seen that this is equal to delta mn. Now, if I look at the inner product between A acting on psi n and A acting on psi n, then we're going to get Cn minus 1 star from this guy, and then we're going to get Cn minus 1 from this guy. So those two together will give me the mod squared of Cn minus 1, and then we have multiplying psi n times psi n. But of course this thing is just 1, so we just have on the right hand side Cn minus 1 whole squared. But on the left hand side I can bring a over here, and that will give me a dagger of a acting on psi n. But this thing on the left hand side is a dagger n is just nothing but the operator psi n. So this is Cn minus 1 squared. So this is going to give us its eigenvalue small n, which we can factor out. So we are going to get psi n, n small n times psi n, and Cn minus 1 whole squared. So this is 1, and therefore we get Cn minus 1 whole squared is n. So we can choose real normalization, and that will be just square root of n. So in a similar way, by considering a dagger acting on psi n and taking its inner product with itself, evaluating this in the similar way, we can find what dn is. So dn plus 1 is going to be square root of n plus 1. So now we can ask, what happens if we keep on applying a? So what happens if we keep on applying a on some state psi n? So let's see that. A, if I apply it once, I get square root n psi of n minus 1. Now if I apply a twice, I get square root of n times a acting on psi n minus 1, which will be n times n minus 1 times psi inside square root times psi n minus 2. So if you keep on doing this, say m times, so a raised to the power m acting on psi n, then we have on the right hand side under the square root n times n minus 1 dot 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 n minus m plus 1, the whole thing under square root, times psi n minus m. So this process, in general will not terminate. Now, we showed before that the eigenvalue n is 0 or positive. So if this process were to continue indefinitely, at some point this eigenvalue of this state would become negative. So this would contradict this result. So the only way this doesn't happen is if the eigenvalue n is an integer, is a positive integer, is a positive integer. And therefore, at some point, this normalization constant becomes 0 because m minus 1 is equal to n, and therefore it becomes 0, and that for critical value, a m acting on psi of n gives us 0, and therefore we do not reach a negative value of a state with a negative value of n. So this means that n is a positive integer, that is it's from the set 0, 1, 2 dot 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 dot,